Okay, one more lecture in this module. Continuing to look at that spreadsheet and diagram that we ended lecture 2 with, and that you're going to play with and work with in the lab. You're going to build your own and replicate some of this analysis and answer some other questions. As an overview, we might think about why a spreadsheet for modeling, something like this. In terms of Powell and Baker, I'm going to sort of do the outline approach to this model, and I'm going to show that that outline approach leads to a pretty easy way of thinking about the algebraic or symbolic version of the model that we might write down. Not exactly like we did with the standard form for the linear programming model, but not all that different. We'll solve that. We'll see that we can get the algebraic solution directly using just the smallest amount of calculus, and then we'll see why spreadsheet modeling is important, and think about at the end, of course, how we might bridge this into uncertainty, because this is our the follow-on from this. Okay, so let's reiterate here on the diagram we have. And so if we were going to outline this and just come up with a variable listing, we might say that profit, let that be I, revenue be R, total cost be C, pi is demanded Q here, V be the ingredients and processing costs. So I'm going to add these two components together to make one variable, and you'll see that that doesn't really affect anything. Fixed cost is the sort of exogenous cost. I'm going to make that italics. And then P is the pie price. That's exogenous, but I mean, it's not exogenous, but I get to choose it. And so you'll see me calling it exogenous in these slides. But remember, it's different. I get to choose that level. It's actually the thing, right? If this is our outcome, this is our lever, right? This is our choice variable, and we are trying to see how, when we make a change to the choice here, it filters through all of this and makes an adjustment there. So yeah, and other than that shortcut where I'm adding these two together, everything here could be a descriptor to match up there to something we call a variable. So the process of building out this as sort of an outlined mathematical model is identical to influence diagramming. We start from the objective and decompose, and so you could say that I is equal to R minus C, three of my variables. The revenue can be broken down into P times Q, price times quantity, two of my variables, again on the right hand side, and then C could be broken down into the fixed cost. It's exogenous, so I'm not even going to bother to make it to use F here. I'm just going to go ahead and substitute the fixed cost level in. And then one other variable, the variable cost, V. And so we went from one equation to two equations, and you can see, right, so something on the we have R minus C on the right hand side of this equation, and we have a new equation down here that defines this part, and this equation defines this part. So if you were thinking about drawing arrows, you would draw them from there to there, and now we're looking in the things that stand out. We have V, Q, and P. So P is under our control. It's the choice variable, so we're never going to have anything that points an arrow to it, but we need something that points an arrow to Q and V, so we need new equations for those. And so these two new equations, if you were to add to this, would be the things we have left to define. So a variable cost equation, and if you look back at that spreadsheet in Lab 2, or look at the handout that goes with this, you would see that V is equal to 2.05 times Q plus 3.48 times Q plus 0.3. This is the processing, and then I think these are the two ingredient items. And so you could add all those up, right? But those are the separate, three separate things that go up with the change in quantity. And then the quantity itself, right, that we had on the right hand side of the revenue equation here is defined as 48,000 minus 4,000 times P. And oddly, as we might have expected actually, the Q, this last equation we're putting in, would have an arrow pointing to these things. So the only thing that's left on the right hand side of any equation, right, So Q and V were left as things on the right hand side that we don't have control over. And so when we wrote those two equations, we actually solved all of our problems here. So Q now is the factor that can change variable costs. So the only thing left on the right hand side is this exogenous choice variable, this thing that's under our control. It's set by us outside of this. Yeah, and so everything else is on the left hand side of an expression. If something's on the left hand side, it means you have it defined in terms of an equation. Now, we can go ahead and solve this. So the nice thing about outlining this in terms of the equations and sort of identifying all the things that we want to solve for on the left hand side and leaving only things on the right hand side that are either defined elsewhere or that are choice variables. And I'm very sorry that this continues to say exogenous here in these slides. That is not fitting with our notation. We are going to solve for that price. You'll see why when you do the lab, why we might consider it exogenous, because I'm going to let you set a lot of different levels for it before we actually solve for it. But we could just go ahead and do those substitutions. So if we have a bunch of things being defined by other equations, well, that's just a call to substitute and reduce the number of equations. So we could try to remove all the endogenous variables from right-hand sides through substitution. So if we recall that price is our decision variable, it's going to be set by a choice, then the demand equation only has exogenous variables on the right-hand side. Price is something we're not going to be allowed to substitute for. But we can substitute in the variable cost equation for Q, right? So if you, I don't know what you call that, the distributive property or something like that. Take all those coefficients multiplying Q and put them together, and then the substitution for Q is actually the demand equation. If you work through that, you'll see that the variable cost equation in terms of the price, the exogenous or the choice variable, looks like this. Okay, now the variable cost equation only has our exogenous or choice variable on the right hand side. If we kept going, we could do that substitution again. So if you can substitute the demand equation into the variable cost equation, you could substitute in the revenue equation, and this is what you get. All right, so P times Q, or now P times 48,000 minus 4,000P, and you get this quadratic. Right, so you get a linear term and a quadratic term, which we probably should have expected because we've already talked in lecture 2 about the fact that when you increase price, revenue goes up because of the direct effect, but the indirect effect is quantity tries to fall, right? Demand falls when price goes up, and so that's going to have a lowering effect on revenue. So there has to be something that describes that kind of quadratic trade-off, increase versus decrease, and that's what it is right there. All the quantities Q are gone from the right hand side of that equation. If we continue the approach though, we can substitute into the cost equation with the variable cost term, and that's what we have here. So if you substitute 12,000 plus V, you substitute the V equation in for that, you end up with this 291,840, 23 through 20p. And we said one more thing was going to be happening when the price changes. The cost term is going to fall. Right, so revenue increase and decrease, right? So competing effects, and cost goes down, and so that's why the profit effect is sort of unknown for us, difficult to conceptually sort of wrap our idea around what price is best. So the current status of substitutions, we have profit is I, revenue minus cost, and we need to substitute for R, substitute for C. When you do that, you end up all the way down here. I is equal to negative 4,000p squared plus 71,320p minus 291,840. We've done what we needed to do. We have described the objective profit only in terms of the choice variable price. It's quadratic in price, right? So we couldn't use our linear model, our linear programming type solver. But we do have plenty of solvers that understand how to solve a quadratic. And then, of course, one of the things we could do is just, if this equation is quite simple to put in a spreadsheet on its own. And so that's what I've done here. So just do some analysis with that math model we have. Substituted algebraic form means the intercept, linear term, quadratic term, and then profit. Okay, so price, this number times this squared, this number times price squared, plus this number times price, plus this negative value, gives us a profit of $27.40. If you increase price to 7.5, the profit goes up. Increase to 8.5, the profit goes up. Increase to 9.5, and the profit starts to fall. The profit falls again. Okay, and so that's what we have. We have the price on this axis, increasing profits, and at some point the price is going up, and the demand is falling too fast for the cost and the increase in revenue to keep up. And so the negative impact on demand is the dominant effect here. It's causing profits to fall. And so you can see why I'm calling this exogenous here, because I'm going to just set different levels of it and plot those out. Okay, so it's under my control. It's exogenous. Every time I plot one of these, it's outside of the model. I'm not solving for it. But why might you call it endogenous is if you have a function that looks like this, there is a calculus application of this model that you could solve and find the best price. Well, one of the ways we might do that without calculus would be to get over in the neighborhood of where we think the peak of this profit curve is and just start incrementing price up, and try to find where it flips and switches. We would never be good enough to be, well, I mean, we might be, but it would be difficult and time-consuming to be exact with that, so we could just do the calculus version, which is this one. This horizontal line here is a way of identifying the fact that there's a peak, right? So you draw a horizontal line and you slide it down towards your curve, and when it just touches the curve in one point, then you have found the peak of that curve. And of course the horizontal line, we say then, is tangent to this curve, meaning the tangent line shares the slope, and the slope of a horizontal line is actually 0. So if we could write a equation for the slope of the profit in terms of price, then we could solve that for 0, and we would know the exact price. We would know the exact location of this point. And that's what we do when we take a derivative. Okay, the derivative is the equation or the function that tells you the slope of this curve at any point. And we know we need to set it equal to 0. So this is the profit equation in terms of price. You take the derivative, the change in profit with respect to price. If you don't remember your rules, trust me, this is the derivative, but it's 2 times negative 4,000 and drop the exponent by 1. Gives you negative 8,000p. 1 is the exponent here, multiplied by 71,320. Drop the exponent by 1. You get p to the 0, which leaves you with just a 1. And so this is the equation to solve. Set this equal to 0, solve for p, and you'll get $8.91.5. So around $8.92 being the exact maximum. So that's our solution. In your lab, you'll get to build that out. You'll get to let Solver do the calculus for you and find that price, and you'll get to do some other work on sensitivities to this. If we were going to evaluate this, then we start from the optimum. We start thinking about how do small changes in other factors affect this. How would we go about in a spreadsheet model or this algebraic model, of trying to understand that trade-off, right? We've already talked about this indirect versus direct effect in the revenue component, and so that might be interesting, right? Understanding that, why is it going up and then falling at some rate? It has to do with that demand equation, we know, and so sensitivity to the demand equation could be something we're very interested in. Knowing how good our demand equation is could be very important, since it's going to define that trade-off. Yeah, and so the spreadsheet version of this model, this algebraic model, gives us a lot, because if you come to me and tell me, you know what, I'm concerned that that number right there, that negative 4,000, that demand slope, is 10% too high or 10% too low, well, then I could get away with maybe changing it here to negative 4,400, But is that right? Is that the only place I would have to change it? Is that the only place the demand curve appears? No, it's in these other things too, right? The quantity got substituted here, so I haven't done it. Oh, sorry, not there. Back here. And so I need that change there. And so essentially you're telling me if you want me to think about a different demand slope, I need to come back to this equation, change it, follow through with all my substitutions to get back to this equation and see what the new price is, but also think about how everything else changed. Well, that, even though it's fun to do the calculus, is no fun. And so that's why we want this model. That's why we want to build this in a spreadsheet. I've got the optimum price. Solver can find that optimum price for me. But if I want to understand this revenue impact, how these revenue values are changing, how some unit cost measure on fruit filling would affect things, I don't want to go back and do all those substitutions. Excel knows how to do all those substitutions, right? You change this number, everything down here updates, and you get the new piece of information. You copy this column 10 times, and you can look at 10 different versions of the model with one thing changed once at a time. And so that's why we do these things in a spreadsheet model. Plus, we have the added bonus that Excel knows how to do calculus, so it can solve for that exact price for us as well. But those updating and sort of doing this decomposition, that's what we're going to focus on in the lab. So your lab is going to, 1, have you build this, and 2, give you a set of scenarios to change this and try to understand the uncertainty. Understand how parameter changes are reflected in the endogenous variables, which is really the idea that's going to lead us to uncertainty. The idea about what do we know, what do we not know, and what is likely to have a big impact, right? Could be that we say, well, we have a very uncertain estimate here, but the model's not very sensitive to it, so it's not worth the investment of sort of adding the complexity. And so that's where we're headed. And in your lab, you're going to get a chance to play out this Simon Pie's model as much as you want with each of the assumptions and track those, and think about that role of demand, think about anticipating how you might deal with uncertainty. And that'll be the end of our lectures this time. So we have this abbreviated this abbreviated module in anticipation of you needing some time to get here and get ready with some other things. We'll also have some of your work on your project required of you this time. So a little bit less on the lecture front.